We were discussing about the multi-carrier transmitter. We'll see a multi-carrier receiver now. This is also taken from textbook of Andrea Goldsmith. Andrea Goldsmith. Wireless communication. Wireless. That is the second reference textbook in your syllabus. Regarding the transmitter, let me just take the transmitter. Yeah. On the transmitter side, you had multi-carrier, which means you had different subcarriers which were non-overlapping. They were centered at different frequencies, and the separation between each subcarrier is total bandwidth B divided by N, which is Dn. And you have N subcarriers, N carriers, or you can call N subcarriers, and they are non-overlapping. Non-overlapping. Their bandwidths are not overlapping with each other, and because they are non-overlapping, they are orthogonal. They are orthogonal to each other. Okay, so each subcarrier is having a particular bandwidth. So it is having this bandwidth. The second subcarrier is having this bandwidth. Third subcarrier is having this bandwidth, and these bandwidths, the separation is B by N. B is the total. B is the total bandwidth, and Bn is the bandwidth of each individual subcarrier. All right. So how can you receive it at the receiver? So how can you detect it? By using just low pass filters. By using filters like this, you can receive this particular subcarrier by using a low pass filter like that. Okay, a filter that passes only these band of frequencies. Okay, these are basically band pass filters. Okay, these are all band pass filters, and you can detect this subcarrier. You can demodulate this subcarrier by just performing a filtering operation. You filter it, filter which passes this bandwidth is going to be Bn. Okay, it is a band pass filter having a center frequency f0, which is having a bandwidth of Bn. It passes this range of frequencies Bn, and this particular subcarrier can be filtered out. It can be filtered using this band pass filter, and you will receive this particular you receive this particular subcarrier here, that is S naught corresponding to S naught of t, and you have some there is also some noise in the channel which is getting added, and after filtering, let's say some filtering noise also will get added. It is N naught of t, and then you do some demodulation. In the transmitter side, you did modulation, either you did some PSKs, phase shift keying, or you did some QAM, quadrature amplitude modulation. Now you do the corresponding demodulation. So it is a signal demapper. The transmitter side you have signal mapper. Here it is signal demapper, and the data rate is R divided by N. R is it was the data rate of the incoming data, and you divided it into different small subcarrier streams, each having a data rate of R divided by N bits per second. And you can use the same carrier which is used at the transmitter, that is cos 2 pi f naught t, to get back the signal, get back the original signal back. Okay, so that is the demodulator part. And then the same process happens along different demodulator chains. So there is cos 2 pi f1t, etc., etc., up to cos 2 pi fn minus 1t. And a parallel to serial converter converts these parallel data streams into the serial data stream. So in total, the output is R bits per second. So one point you want to note is that this multi-carrier communication doesn't change data rate. So MCM, it doesn't change the data rate. Doesn't change the data rate. That is something you have to keep in your mind. You have more than one carrier, but the data rate is not changed. That is some point you want to note. And in practical implementation, okay, and yeah, one more thing I want to tell is uh, each of these subcarrier, they experience flat fading. That is in the diagram which I drew in the last class. Each of the subcarrier, they undergo flat fading. So this particular subcarrier, it gets multiplied with a particular frequency response h of f naught. So f naught, signal at f naught getting multiplied with frequency response of h of f naught, and this will get multiplied with h of f1, etc., etc. So essentially, they each subcarrier, each of the subcarrier, they undergo flat fading. They undergo flat fading, or yeah, if I denote channel gain by alpha I, alpha is equal to h of fi. Okay, they undergo flat fading. Each of the subcarrier undergo flat fading because the bandwidth of subcarrier is very small when compared to the total bandwidth of the channel, total bandwidth of the signal. Okay. Now, in practical implementation, okay, I'll give you some time to take down this diagram. Okay, please take down the diagram, and once you have finished taken down the diagram, you can just intimate me in the chat box.
Okay, sir.
All right. Now, in practical implementation, what happens is, so now you would see what is the total bandwidth of this particular transmission technique. What is the total bandwidth consumed? Okay, let us see about that. Etc. etc. I can have this is fn minus 1. You have n subcarriers, so this is fn minus 1. What is going to be the total bandwidth of this transmission. What is going to be the total bandwidth? Uh, you would think that this is this is b divided by n, and as such you can have there are n number of, so b is equal to, or I can write this is 1 by tn. So you would think b is equal to 1 divided by tn, but this is not the case. Okay, in practical implementation, practical practical implementation, what happens is for the pulse shaping, that is g of t, for the pulse shaping, raised cosine pulses are used. Raised cosine pulses are used. Raised cosine pulses are used. So when raised cosine pulses are used, there is it is somewhat like this. Raised cosine pulse may look like this, and it has something called a roll-off factor. Okay, some extra from this pulse shape is not good. Something like this, and it has something called a roll-off factor. From the actual time, it takes some time to some uh, time to come to zero. So that is this roll-off factor beta. Okay. In fact, both of these contribute to beta. So beta is a roll-off factor. And why is this roll-off factor coming into picture? Because uh, that is the same question why you are using a raised cosine filter. So you cannot transmit a signal with abrupt transitions like this. You cannot, the time domain, you cannot transmit a signal like this in a channel, because channels are band limited. Channels are in general band limited. So if you take because of this abrupt transmissions, you can see that the bandwidth goes to infinity for this type of signal. So when you use a raised cosine filter like this, you will have soft transitions. You will have transitions which they are not very sharp transitions. So because of this uh, soft transitions, there is some roll-off factor. There is some roll-off factor, and this roll-off factor will also contribute. This roll-off factor will also contribute to the pulse shape. Right? So that contribution is beta. Okay, let that be beta. And one more thing is, in order to time limit, for time limiting the pulse shape, even this raised cosine filter have some tentacles like this. They have some, after reaching zero also they will slightly continue. When compared to a sync pulse, the amplitude is less, but they will have small transitions like this. Okay, in order to time limit that pulse shape, some additional time limiting factor epsilon by Tn also has to be included. This is a time limiting factor. So this pulse has now, if I draw the pulse frequency, okay, so this is one subcarrier. Let's say it is one subcarrier. It has got, what is the bandwidth of one subcarrier? In practical implementation, the bandwidth of one subcarrier Bn, it is going to be, there is 1 by Tn, of course there is 1 by Tn, which is the original bandwidth of the signal. Also there is this beta by Tn, which is the roll-off factor. You have epsilon by Tn. Epsilon by Tn is the time limit factor. So that is 1 plus beta plus epsilon divided by Tn. That is the bandwidth of one subcarrier. It is the bandwidth of, this is the bandwidth of one subcarrier. It is the bandwidth of one subcarrier. So how many subcarriers do you have? You have n number of subcarriers. Alright. So you have n number of subcarriers. So the bandwidth required for multicarrier communication, multicarrier MCM, going to be 1 plus beta plus epsilon divided by Tn, which is the bandwidth of one subcarrier, and like that you have n number of subcarriers. So n into 1 plus beta plus epsilon divided by Tn. Right, that is the bandwidth of the whole multicarrier transmission. So here you can see in practical implementation, this whole bandwidth required for the subcarrier transmission, it is 1 plus beta plus epsilon divided by Tn into n. Okay, so you have n number of subcarriers, and these subcarriers are not overlapping with each other. So a subcarrier ends, and at that point itself the next subcarrier frequencies begin. So B is equal to 1 plus beta plus epsilon divided by Tn into n. Okay, and that is one very important thing you have to keep in mind. And you can also see these type of equations in the problems which you are going to do. And what are the disadvantages of this type of multi-carrier transmission? So disadvantages of non-overlapping subcarriers. Okay, what are the disadvantages of non-overlapping subcarriers? One of the main disadvantage you can see here is that these subcarriers, they are band limited. They are band limited to Bn, and you need the receiver, the band pass filter you have here, BPF, the band pass filter you have here is having sharp edges, because you need to take in only this signal. Okay, you want only to have this signal. So you are having very sharp, very tight filtering here. Okay, you can call it a sharp or a tight, very tight filtering happening here, and it is very difficult. You would have learned in digital signal processing that it is very difficult to uh, design a tight filtering, a filter with very sharp transition. It is very difficult to design. So that is one of the disadvantages of this type of uh, uh, non-overlapping subcarriers. You can see that if the transition slightly it happens to this side, okay, if the transition is not sharp, if the transition slowly extends to a little more frequencies, then the other subcarrier also comes into this picture. Okay, the information the other subcarrier also will try to interfere with this symbol, and as a result inter-symbol interference happens. Okay, another phenomenon called inter-carrier interference happens. Okay, there are two different carriers, and uh, if the low pass filter, if the band pass filter is not tightly designed, if the band pass filter is not having sharp edges of transition, then inter-carrier interference, it is called inter-carrier interference. It's not mentioned in the textbook. Inter-carrier interference happens. Interference. Inter-carrier interference happens because the information in two carriers get mixed up. Okay, okay. And this is the first disadvantage I want to say. The this type of non-overlapping subcarriers need tight filtering. And what happens if if there is no tight filtering, the orthogonality of subcarrier is lost. Okay, because the other subcarrier gets added with this subcarrier. So the orthogonality is lost. If there is no tight filtering, orthogonality is lost. And the second point is that here you actually need only a bandwidth of 1 divided n divided by Tn, right? Because you have n subcarriers, each subcarriers are having a bandwidth of 1 by Tn. But because of the pulse shaping, you have additional roll-off factor beta. Because of time limiting, you have this factor epsilon. So because of all that, you need additional bandwidth. Okay, so what is the excess bandwidth you are trying to use here? So excess bandwidth you are trying to use is beta plus epsilon divided by Tn into n. So much of extra bandwidth on each subcarrier, right? So you are using so much of extra bandwidth here. So that is the second point I want to make. The second disadvantage is it is spectrally inefficient. It is spectrally inefficient because you are using a lot of extra bandwidth here. Okay, because of the roll-off factor and because of the time limiting factor, you have to use extra bandwidth. Even when you need only n divided by Tn, so you have to add this quantity beta plus epsilon divided by Tn into n in your bandwidth calculation, right? And the third point I want to make is you can see how many systems are there in this demodulator, in this receiver and transmitter. So in the transmitter side you will have n number of transmitters, right? N number of modulators, n number of you usually call this as chains. Okay, these are communication chain. Yeah, this communication chain will contain a low pass filter. It will have a demodulator. It will have and you can have you should have n number of band pass filters. Band pass filters centered at n number of different center frequencies. You need n different demodulators. Okay, in the transmitter side, you need to have n different modulators. You need to have n different carriers. Okay, there should be oscillators which generate these carriers, and there is a lot of devices required for this type of a transmission. So that is the third point I want to make. Let me consolidate everything here. The first disadvantage is that it requires tight filtering. It requires tight filtering, which means very sharp filtering. Okay, and it is very difficult to design bandpass filters which have this tight filtering. And if it is not satisfied, if tight filtering is not satisfied, then what happens is loss of orthogonality between subcarriers. Loss of orthogonality between subcarriers. Okay, loss of orthogonality between subcarriers. The second point which we discussed was spectrally inefficient. Spectrally inefficient. Because you have the Roloff factor beta for each of the pulse. You have epsilon, which is the time limiting factor for each of the pulse. So you need to use excess bandwidth. Excess bandwidth is required for transmission. Required for transmission. And the third point is that n number of independent modulators and demodulators are to be used. See, not only modulators and demodulators, what about the associated circuitry? Everything has to be independent, right? So each of the data stream is independent. Correspondingly, each of the communication chain has to be independent. If you have n number of subcarriers, you need to use n number of communication chains, right? If what if n is a large number? N is usually a large number in order to make the coherence, in order to make the bandwidth of subcarrier much less than the coherence bandwidth. In general, this value of n is very large. Suppose n is 64, then 64 number of modulators and demodulators. It's very difficult to keep so many communication chains in a particular multi-carrier transmission. So all these are disadvantages of multi-carrier transmission. Right? Let us see how we can overcome these disadvantages, how we can design something which is spectrally spectrally efficient, some system which doesn't need tight filtering, a system which doesn't need n independent modulators and demodulators. Okay, and all these leads to the formation of a technology called orthogonal frequency division multiplexing, which revolutionized the wireless communication industry. And OFDM, orthogonal frequency division multiplexing, doesn't need tight filtering. It is spectrally efficient. It just needs one modulator and one demodulator for any number of subcarriers. Okay, so we haven't reached OFDM yet. We are still in this multi-carrier transmission. We haven't reached there yet. Let us try to do some problems now and understand how we can to understand more about multi-carrier transmission. So this is one of the example problems in the textbook. Consider a multi-carrier system with a total passband bandwidth of 1 megahertz. Okay, don't take down the question now. Okay, just you can just listen to me. You take down the answer. You take down the main points and you take down the answer. The question is there in the textbook, and I've shared the textbook with you also. The total passband bandwidth B is equal to 1 megahertz. Suppose the system operates in a city with channel delay spread 20 microseconds. The delay spread of the channel is 20 microseconds. How many subchannels are required to obtain approximately flat fading in each of the subchannels? Right. So from here, from the channel delay spread, we are able to find the coherence bandwidth, that is BC, which is equal to 1 divided by Tm, that is 1 divided by 20 microsecond, which is 50 kilohertz. So 50 kilohertz is the coherence bandwidth. and you have to design the system in such a way that your subcarrier bandwidth Bn is less than Bc. For that, I take this condition Bn is equal to 0.1 Bc. Bn is equal to zero point 0.1 Bc. Right? Thus, what is n? N is going to be, you know the equation, Bn is equal to B divided by n. So n is going to be B divided by Bn. So B divided by Bn, which is going to be, the total bandwidth is 1 megahertz divided by Bn. Bn is equal to 0.1 Bc. So 0.1 into Bc is given as 50 kilohertz, 50 kilohertz, and you have 200 subchannels which are required to ensure flat fading on each subchannel. So if we had taken Bn is equal to 0.01 Bc, again you would have got a flat fading subchannel. But we haven't taken so far. 0.1 Bc is sufficient. So it is like the coherence bandwidth is divided into 10 different segments. It is divided into 10 different segments, and now each segment might have flat fading. It is approximately flat for that range of frequencies. And mostly this works out. But later when we study OFDM, you will see that if you want to implement this discretely, for discrete implementation you use OFDM. In OFDM, this value of n must be a power of 2. Okay, n must be a power of 2. And when you say you need at least 200 subchannels, then the power of 2, which is greater than 200, is 256. N is equal to 256. Right? N is equal to 256. Okay. So you note down the main points. I'll share the video with you. Okay, you're finished?
Yes, sir.
Okay.
Noted.
Okay. Let's move on to the next problem. Consider a multi-carrier system with Tn is equal to 0.2 millisecond. The multi-carrier system is having a, this is the symbol duration of multi-carrier. It is the symbol duration of multi-carrier. It is 0.2 millisecond. And Tn is greater than delay spread. That is what we want. Tn much greater than delay spread. So it is a condition of no ISI, no intersymbol interference. So each subchannel experiences minimum. Okay, it is written here. Assume the system has n is equal to 128 subchannels. Okay, the value of n is equal to 128. If time limited raised cosine pulses with a roll-off factor beta equal to 1 are used, and if the additional bandwidth required because of time limiting to ensure minimal power outside the signal bandwidth is epsilon equal to 0.1, then what is the total bandwidth of the system? Okay, you can directly apply this equation you have found here. B is equal to n into 1 plus beta plus epsilon divided by Tn. Substitute these values and you can very well get this result. Okay. Okay, did you understand the idea behind this?
Yes, sir.
Okay. Yeah. All right. That's about multi-carrier. Multi-carrier with non-overlapping subcarriers. If you have any doubt regarding ഇത് കഴിഞ്ഞിട്ട് we are going to overlapping subcarriers, which is OFDM. If you have any doubt so far, you can ask.
കുഴപ്പമില്ല സാർ എന്നിട്ട് മനസ്സിലായി.
Okay. Uh, so we'll do one thing. We'll stop for the class for today, and for the next class we'll start with overlapping subcarriers, which is giving way to our OFDM, orthogonal frequency
Okay.
division, OFDM transmission.